All right, your lab logbooks. Remember, you got to keep your table of contents up to date. That's not my job, that's your job. Keep your page numbers, the dates. Date should be year dash month dash date of the month. So yesterday was 2019-08-27. Whenever you're doing any data in the lab, any lab observations or measurements or procedures that you're changing in the lab, then you need to have the people in your lab group sign and date at the bottom of the pages. Okay, for any page that they are a witness to. Okay, so they are witnessing and saying, yes, this is valid stuff you did actually in the lab. So procedures and hazards you do before the lab, don't need to worry about that too much. Not as far as the signatures are concerned. It's important to have that, but it's not necessary that you have a signature on that. In fact, you shouldn't, because they did actually witness you doing that. Okay? So let's talk about the lab that we did yesterday and what we're going to do with the post lab. So you should have written a post lab already. Let's see here. Here we go. So I tell you what, before we even get into that, let me point out about something tomorrow, so we're working. I don't forget about it later in this in the period here. We're going to be doing a debate discussion tomorrow. Set this up so it's a little bit easier to see here. Just lay one down. Okay. The instructions are here. It tells you what you're supposed to do. You want to do some research yourself on the internet tonight on the nature of science. There are some key categories that you're going to be looking up things about. And after the debate, you'll be expected to turn in a list of sources in a bibliography. Not a whole report, just a bibliography. Okay? We're going to practice doing citations. All right? So I've got a template for you here to do that, but there's almost nothing there for you to guide you in that. So you've done citations before. You've done bibliographies before, okay? The form of bibliography you want to use in this class is American Chemical Society, ACS. Now, most of what you do what do you use in most of your English classes? What citation format? MLA? Okay. That works reasonably well. Okay, there's just some little changes you need to make in ACS, but look up ACS format and follow a pattern that somebody else has laid out for you there. Okay, there's some links to that in the instructions. It's not hard to do, but you've done bibliographies. I can't even say it. Bibliographies before, or works cited pages before. Okay, ACS is kind of forgiving in that there's a lot of different ways you can do citations and still be within the ACS format. Okay, so just read what's there. You have to have, when you look up a source, you need to have an author. If the source doesn't have an author, it's probably not a valid source anyway. Now that's not to say that there aren't organizations that as a group are the authors, okay? So make sure that the organization that's giving you information, in this case on the nature of science, is a valid organization, okay? You want to make sure that you're using sources that are not just, pop sources, okay? Just the people that they should know what they're talking about. That makes sense? Okay. Never depend on just one source. If it's possible, in this case, you're looking for the nature of science. If you only look up one source for this information, you're not really getting a good overview of what we're discussing. And it is a discussion. You're going to get a grade for participation. I'm not going to say, Sam, what do you think? Joe, what do you think? Susan, what's your opinion? I'm not going to do that. You're going to have to jump in there on your own to get credit for participating in the discussion. Okay, and it is a discussion / debate, and I welcome being nice. Okay, being polite, but disagreeing. That's something we do in the sciences. If you disagree or have a question, about it that you think, wait a minute, that doesn't make sense. What is, ask the question. All right, but just be polite. We don't want to call names or give people a hard time. All right, so we're going to be doing something, a discussion, trying to figure out for ourselves what science is. Okay, some things that you need to, in addition to what is science, the big question, sort of some subcategories within that is how does science differ from other things? Critically, you need to know the difference between science and pseudoscience. Okay? So don't look for one definition. Get some people, some sources that are reasonably valid, and get a good idea of what pseudoscience is. Don't just come in and say, well, it's fake science. That ain't gonna fly. Okay? That's not really telling me what I need to know, what we need to know, what you need to know. Need to know the difference between pure and applied science. Okay, that's another category. What is it? This is about science, and there is a pure science, and there is an applied science. Well, what's the difference? Okay, so just read the instructions there. I hope they're pretty clear. I've been working with them and modifying them for several years now because we do this every year in the honors classes. So just read what's there. Follow the instructions that are there. All right? Now, let's go to saltwater density now. So you're supposed to have turned in a report last night before 8:20 this morning, and you put it on this template, and the instructions are all there. Just to reiterate, when we're doing lab reports in here, you're only being expected to do certain parts of a lab report. We're not doing a full formal lab report, but you're practicing in certain categories. So you get good at each category, hopefully. There are a lot of instructions, individual specific instructions about each of these things in the lab report document. But as we go along in future lab reports, I'll give you templates that have less and less information. So I'm expecting you to learn this stuff as you go along. So if I tell you today, this is the format for a hypothesis, the next time you can write an hypothesis without those instructions because you've already done it once. When I tell you this is how you do a graph, then I expect you to do that next time without those specific and detailed instructions because you've done it once. Okay? But we're going to clean up some of the graphing and table stuff today. All right? Going over the reports that I've seen so far, there are some issues that I'm seeing with the lab reports. With the tables and the graphs. So we're going to go look at all of that. All right? So if you have your report and you've submitted your report, let's unsubmit it so you can work with it. Okay? So you go and find your report, or go into Google Classroom and find the report and unsubmit it so you now have access to it and can edit that document. Okay? I'll give you a minute to do that. All right then. Let's take a look at a few tables and some issues that I see repeating themselves as people do tables. Table labels. Okay, every table has to have a table number. If there's more than one table, it's table 1 and then table 2 and then table 3, followed by a period. Then you have to have a 1 to 3 sentence description of what's the table is about. If you need a guideline on what goes in a table description, I give you a sort of a simple guideline. Tell me what's in the table and why it's important, right? So you're trying to inform the reader. If they're just looking at that table and haven't read anything else in the report, they know what the table is for and what's there. Why did you do this table? Okay? So if I'm looking at the data that I just grabbed somebody's today and put it in this little thing here so we can kind of look at it. If I'm looking at this information and I'm trying to write a table description, I might write something like, this is data, or these are measurements. Taken in a lab on 2019, month is August, date is 27th. And I'm making different concentrations of salt water. I might even want to be clear about which kind of salt, but I know more about this than you do right now. So this is specifically table salt. So that's NaCl. And the resulting change in density, maybe. Okay, that might be what I'd say about it. All right, why is it important? Because I'm collecting this information to find out about concentration and density. What's in it? Concentration and density and the measurements that make it up. That makes sense? Okay. I really don't need anything else if I were writing this table label. Now, I want you to write your own table label and not use mine. Okay, I've given you an example now. Okay, you write it in your words, write what you would say about it. But basically, you're trying to say that. If you copy word for word what I've written here, that's plagiarism. Okay, unless you cite me as a source. I don't want you to do that. I want you to write your own table label. Write it in your own words. What's there? Why is it important? Why did you include this data? And saying I included this data because Mr. Tedder told me so, that won't fly. I'm sorry. Come on. All right? So then you've got the data you've gathered. Okay? In this case, they say they've weighed out 0.5 grams of table salt. Anybody see any problems with that? Huh? Well, you put a 0 in front of it so that you can clearly tell where the decimal place is. It's just that's more of an editorial decision, but I would rather see a 0 in front. Anything else? Not supposed to have the units of measurement, so they have included units of measurement in the table label. In fact, I did that for you because this is your first table you're doing for me, and I want you to put your units of measurement in the column labels. Okay, you can't put the units of measurement in the cells. All right. Anything else? Well, what I see is they did not use the correct number of significant digits. They didn't measure properly. They didn't record the measurements because this was on a digital balance. And on the digital balance, if they measured out 0.5, the balance says 0.50. You have to write down all the digits. You have to record all the digits. So they didn't use all the digits. That makes sense? If they're not recording all the digits, then they are not telling me the precision to which those measurements were made. That is required. All right? So I know that the balance doesn't say 1. It says 1.00. Okay? Now, this column right here would be the volume of the solution, right? So let's say volume of and we measured that in milliliters. It is good practice to write the units of measurement for milliliters as a lowercase m and a capital L. Most base units in the metric system, if the unit of measurement is not named for someone, it's a lowercase letter. So that would be a lowercase l, because liters aren't named for a person. However, it's hard to tell the difference between a lowercase l and the number 1, or the capital letter I. Okay, so just for clarity, it's accepted and expected that you write liters, the symbol for liters is a capital L, okay? But the modifier, milli, says that's a thousandth of a liter. We use that lowercase m. If it were milligrams, it would be both lowercase m and lowercase g. But L is kind of a special case, okay? We haven't talked about significant digits in this class yet, but the problem with the measurement they have here is that these measurements in the column for mass, well, that would be right. No. Actually, no, there's a problem with the volume here because they've got too many digits. The graduated cylinder you're using in this lab had markings at the ones place. That is to say, there's little slashes on the side where you have 25 or 26 or 27. So there's no little marks on the graduated cylinder for the tenths place, right? So you can only estimate one more digit than the markings on the device. You can't estimate two more digits than the markings on the device. That makes sense? So they have too many digits here. You've got to be careful about the digits. That's important. Oh, yeah, hang on. All right. The last column is where they calculate density. So this is density of, we could say, saltwater solutions. Now, since I've already defined saltwater as being NaCl, I don't really have to say it over here, but it doesn't hurt to do that, okay? We need to have units of measurement. Density has two different units of measurement. You're taking the mass and dividing by the volume. Technically, any mass measurement and any volume measurement are reasonable, would make up a reasonable density. But in this case, we have a specific mass and a specific volume. So we took mass in grams and we divided by volume in milliliters. Okay, again, lowercase m, capital L. That makes sense? Now we're going to talk a little bit later in this class about how to get the correct number of significant digits in the answer over here. Basically, when you're doing division, mass divided by volume in this case, we're dividing. We can't have more digits in our final answer than the digits that were in the numbers that were used to calculate that. So since the mass was in 4 digits and the maximum number of digits for the volume here was 3 digits, then we want our final answer to always be in 3 digits. Okay, so this is the density that I gave you. All right, here they're putting too many digits. We're going to take one of them off and round, in this case, round up. Okay, let me go back and show you that again. So if they have 8 here and I round off the 8, that means this is supposed to be a 9. That makes sense? Rounding up from, if you're getting rid of a digit in the first place you're getting rid of, 5 and above you round up. Yes? No? Everybody understand? Okay. All right. So that's some of the problems with that data table. Here's a data table Any problems anybody sees here? They put units of measurement in the cells with the numbers. You can't do that. Units of measurement only belong in the column labels. Okay? Anything else? I see that they have a density over here with no units of measurement. I see that they have the mass of the table salt and the mass of the salt water, but where's the volume of the salt water? If you're calculating the density, that's got to be mass divided by volume, and they don't have any record of volume. Does that make sense? At least right now. They might go and fix it. Anything else you see wrong here? How about the table label? It's not there. Okay, you always have to have a table label, or it's not a table. Okay? Make sure you include a table label. Okay, let's look at this one here. Okay, anybody see anything, any problems, any good things or bad things? Or we should just stick with the bad things. I don't know. Okay, what needs to be changed or what's good here? I can start calling names to get you to speak up, but I'd rather you just speak up because you're just trying here, all right? Huh? Here? Or here?
No.
Oh.
Like
Number 3, here.
Yeah.
Okay.
Shouldn't it be 1.00?
Well, you need to have the right number of significant digits or the number of certain digits, certain and uncertain digits. So the balance would have 1.00 exactly. Even the 0 here should be 0.00. Okay. What else?
And the 4 one, shouldn't it be 15.50?
Yeah, you're right. You have another digit here. Okay. Volume. How about volume? Yeah, if your graduated cylinder has markings to the ones place, this 5 is in the ones place. Okay, this 1 here is in the tens place. If I had another digit to the left of that, that'd be in the hundredths place. Okay, since the graduated cylinder is marked to the ones place, then I need to estimate one more digit. All right, and that doesn't mean just putting in a 0. It means actually estimating where the measurement is between the markings. So if it is on 15, they should be saying 15.0. Okay. They don't have, I see, they have the units of measurement here, but we want to make them clearer than that. What is that, MI, M1? What, see what I'm saying? Hard to tell what it is. And I purposefully used this particular font so you can't tell the difference between a lowercase m and a capital I and the number 1. Okay? So we want to change this so we have a lowercase m and a capital L. Okay? How about the density description here? No units of measurement. You got to have those. All right? We really need to have 3 significant digits, but again, we haven't gotten to that instruction in this class at the time I'm recording this anyway. All right, let's go down here and look at this one. All right. So this is a pretty good one. They've done a pretty good job laying everything out here. All right. We don't have units of measurement quite right yet, but the descriptions and the column labels are pretty good. The table label's pretty good. Okay. They've been careful. They've been clear and detailed. There's a point where you can be overly detailed in a table label, in a description, but they've done a pretty good job here, All right. Let's see. I thought I had one more on here. I guess not. Okay. All right. They actually did their own density for pure water, which turns out for yesterday's lab was a good idea. Okay. Let's take this data here. In fact, I tell you what, let me go ahead and I'm going to So I can show the next class where we were. I'm gonna take all these changes out that I made. Okay. Go back down here. We're gonna put these into a table, into a graph so you can kind of see how that works. So, actually, they didn't put the mass right, did they? It should be 1.00, 0.00, right? So that is a problem, but the data set, the measurements are pretty good. I want to use these data, this data they've included here, okay, for a graph example. Let me pull up Logger. Okay, so here's just a page for Logger Pro, and for a lot of labs, we are going to be given basically templates. In this case, I want you to see how this works without having a template so you can fix things that need to be fixed. Do not trust the templates to have everything the way that I want you to do them. You may have to change titles and axes labels and such, okay? So make sure that you're careful about that. All right, so let's go and find the table. So here's the table I want to use. I've highlighted this row, or this column rather, of data. I'm going to right click and copy. You can copy it in any fashion that works. There's several different ways to do that. I'm going to go to this column here under X and right click and paste. Okay. Now notice when I take it from a table in a grid that's in a Word, or in this case, Google Doc, it sort of leaves the first block blank. Okay, we'll get back to that. I'm going to go over here, back over here, and grab the last column, because what I want to compare is the amount of salt in a fixed amount of salt water, or, solution, to the density. So I want to highlight this and copy it. Go to Logger Pro, go to the top cell, and paste. And so it leaves the top cells blank. All I have to do is click those two cells, right click, and click delete cells, and it's cleaned it up. Okay? Now, let's look at the graph. Please give me your full attention here. Okay? I know you're trying to do it at the same time, but if you're so focused on your screen you're not seeing what I'm explaining, you're going to be asking me to do it again. All right? One of the things is these dots are kind of hard to see. You don't have to change them, but I'm going to change it so you can see more clearly what I'm doing. And when you're copying and pasting your graph, it'll be a lot easier for me to read and tell what you're doing if you do it right. So I'm going to right click. I'm going to mouse over any one of these dots, right click, and click graph options. Well, wait a minute. Hold on. Let me see if that's right. I'm sorry. Left click, I guess. No. Yeah, left click. Options. Okay. I said right click. So any one of the dots, left click, double click, and you're going to get something called manual column options. You see that? Okay. Over here, options, instead of empty circle, I want to scroll up and say I want a filled circle instead. And then just so you can see it, I want to make them large. Now we can see the dots pretty easily. Okay? Got that? Now if you publish a graph like this, you're going to lose points. The problem is that the data is not spread out so you can see the pattern. All right, we want the data, we got all this white space up here with absolutely nothing in it at the top. The top, 9/10 of the graph area. All right, so what you can right click and tell it you want to auto scale. Okay, so I'm going to click in the graph area, right click, auto scale. And I'm not going to auto scale from 0. There are a few graphs where auto scale from 0 is a good idea, but 99% of the time, auto scale without doing it from 0. I know that's what you're used to doing in math classes, but we don't automatically assume we want to keep the 0 point because sometimes that's a lot of wasted space again. So you can see it spread everything out. Okay? Now the only issue with this is I've got a data point way up here in the corner and way down here in the corner, and you could almost miss it if you're not paying attention. So I'm going to move those data points away from the corner so you can see where it is. Okay? So I'm going to take my cursor, my mouse down here, and I'm going to drop down below the x-axis down here, you call it, the horizontal axis. And you see there's a double arrow, squiggly double arrow down there. If I move to the right, eventually it becomes a single arrow with a line on the backside. If I left mouse click and hold it down, I can pull that data point down, back away from the edge. Okay? If I go over here and drop it on this side, I've got a squiggly line, a squiggly arrow with a line, and I can hold down the left mouse button and pull it back from the edge. Okay? I can do the same thing on the vertical axis. If I'm right here in the middle of it, that double arrow squiggly moves everything up and down. I don't want to do that. What I want to do is to go down here near this bottom and get this symbol where I have a squiggly arrow with a bar and left mouse click and just pull it back from the edge. And this dot up here in the upper right, I want to pull it down in the same way. Now I can clearly see where all the data points are. Does that make sense? All right. Does this look like a straight line or a curve? It looks more like a straight line. If your data points are a perfect straight line, you're probably cheating. Okay? In the lab, you almost always have errors somewhere in measurements. It's just never going to be perfect. But you can tell the pattern is pretty much a line. That's why it's important to have enough data points so you can tell what the pattern is. If you've only got 3 data points, you can't tell if that's a straight line or a curve. You need enough data points to tell what's going on. Okay? Generally, we want to do 3 measurements for each of these concentrations, but we don't have time to do that in some of our labs. So by doing enough data points, we can tell. Upper part of the Logger Pro are these icons up here. You've got one that says curve fit, the one to the left of that says linear fit, one says integral fit. If all we need is a straight line for best fit, we can just click this icon right here that says linear fit. If you mouse over it and leave it there for a minute, it'll put up a label that says linear fit. All right, that means a line, linear. Okay, and we'll click that, and there's the best fit line. That tells me what the pattern is. Okay? This best fit line then is what I'm going to make judgments about my unknown about. Yes?
Can you show us how to make the dot solid again?
Can you tell you how to make dot solid? Okay. Mouse over the data points. Double left click. Okay, so mouse over the data points, double left click. You're going to get this dialog box that says Manual Column Options. Look under the tab that says Options. Click this little down arrow and choose a filled shape instead of an empty shape. Okay? You can use squares or triangles if you want to, but it's just easier to see the filled shape. I also changed the size from medium to large. You don't have to do that, but I did because I want my graph to be easy to understand. All right, I want it to be clear, and clarity is important when we write in the sciences. Now, if you have a curve or a straight line, and this dialog box here is on top of your line or any of your data, just mouse over it, left click, and move it wherever you want it to be. Okay, so that it's not in the way of your seeing a pattern or data points. All right, now, so I've got a graph now where I can take the unknown, the sample that I gave you that had salt dissolved in water, but you didn't know the concentration. You only knew the density because you calculated the density. You measured the volume, you measured the mass, you divided the volume or mass divided by volume. If I go over here and find that density, I can check where it intersects here and find out what the concentration is by going down here. Okay? Then, this data here I have is my calibration curve. Okay? Or it's also sometimes called a standard curve. All right? I have created a set of concentrations for which I know the density. I know the concentration, I know the density. I've got a graph. If I have a solution for which I do not know the concentration, I can look at where the density is over here and just use that standard curve to find the concentration. Okay? Just horizontal line over till you intersect the best fit line, and then scan down with a vertical line to find out where it is on the horizontal axis. All right. Let's see. I don't remember somebody give me a density they got for the unknown. You have your data there, right? Yes or no? Just give me a density. Raise your hand if you calculate the density. All right. What density did you get? 0.9934. Okay. So I have to find 0.99. Let's see, this is 0.95, 96, 97, 98, 99. So slightly above that. I scroll over here. It intersects with the best fit line about here, which means I've got a concentration of about 2.9 just by visual inspection. That makes sense? Because here's 1 on this marking, here's 2, and here's 3. So make sure you're careful about where the markings are. Now, there's a neat little thing you can do. I can go and, let's see, can I do it this way? No. So let's go over here to Analyze. Do you see on the toolbar where it says Analyze? We'll click Analyze, and let's click, I think it is Examine. Now, wherever my mouse is a vertical line. And look, there's a little dialog box next to it. You see that dialog box right there? I can tell on Y, 99 what did you have? 9924. So I want to try to find 99. Well, it's not changing for some reason. Let's try this. Let's do this again. Analyze, examine.
Thank you.
Oh, it's using the actual data points. Wait a minute. Interpolate? Yeah, interpolate. That's what I need. I'm sorry. Not examine, because that's going to go with the data points. Interpolate's going to use the curve. So click Analyze, Interpolate. Okay? Analyze, Interpolate. All right. Now it's going to give me exactly what's on the line. So if I look at that dialog box right up here, and I'm 992, and you can see it's got more digits, so I have to choose what I think is the best point in there. It'll tell me what the horizontal axis value is. If you're rounding off, it's going to be pretty close anyway. I need 3 digits. So I could say the concentration is going to be 0.277 grams in whatever value or amount. They use 90 milliliters, I think, in their solution. So you have to look at the volume you had. That makes sense? So that's an easy way to find the actual volume or the actual concentration using a tool that's in the graphing program. Now you can do it visually. You can print it out and use a ruler, but I can do it with this pretty easily. right, that's a little helpful thing. All right, let me take that away, interpolate off, because I want to finish the graph the way I need to publish it. Okay. The axis down here, the x-axis is not labeled properly. I'm going to go over here to this organizing chart and double click on X. And I want to fix what I'm calling X. So this box here that says this dialog box, that I'm going to click the tab that says column definition under name. Let's see, this is mass of NaCl and I think, if I remember right, they had 90 milliliters of saltwater solution. If I can spell right, saltwater solution. Okay. If I click done, that label is going to come up down here on the bottom. You see what I did? So I'm going to go back to X now. I'm going to double click it again. And you don't have to do it more than once. I just did it that way so you can see that it changed. The short name is what's at the column of this. This is not a table because it's not a formal table. It's a chart. I'm just going to call this mass NaCl. You can call it mass salt, whatever you want to, because we don't really need it. It's just there for your convenience. Now when I click done, this title over here on the table changed. It's no longer saying X. Okay? All right, I need to fix something else. I'm going to double click again. Again, you can do this all at one time. I'm just showing it to you one step at a time. I want to put units of measurement in there. Well, what units of measurement did we use for the mass? So I just put in a G, hit enter, and now I've got G in parentheses on this horizontal axis. Make sense? You do the same thing with the vertical axis. What was on the vertical axis? Density. All right. Actually, that probably ought to be two separate words, I guess. I don't know if salt water can be one word or not. Short name, I'm just going to put in D for density. Again, I don't need the table itself. I just need to label it. And what units do we use for density? In this case, grams per milliliter. Okay. If I click done, now my vertical axis is labeled properly. Okay. All right. Let's put in a title. There's several ways to change the title. The easy way that I like to do it is I move my cursor, and you can, if you look carefully, there's a plus sign on the screen. I'm going to slide it up, and when it crosses that top line, the boundary of the graph, it becomes a finger pointing thing, okay? I'm going to double click there, and it gives me an option to write a title, a dialog box with a fill in the blank that I can use to put in a title. Now, what's the format of a proper title for the sciences? The effect of independent variable on the dependent variable, okay? So the effect of, and the variable is a change in the amount of salt. In this case, for them, not you, your volume may be different. For them, they use 90 milliliters, okay? So the effect of changing salt concentration, that's just the way I'm going to word it. Okay, you can say the effect of salt mass in certain volumes, whatever is telling me what the independent variable is. Okay, please don't use my title. Write your title. Okay, the effect of changing salt concentration on the density of solutions. Okay, that's what I'm going to use. Again, write your own title. Okay, but the effect of independent variable on the dependent variable. Listen, if you're just copying down my title, you're not learning how to write titles. You're just copying something. Okay? I mean, you can follow lemmings off a cliff. I don't know if y'all know that. That's a myth, by the way. It used to be a common myth. And you die just like the other lemmings do. Okay? And y'all can look that up. Look up lemmings.
What is a lemming?
Huh?
What is a lemming?
Well, look it up. That's what the internet's for. Not right now. Okay? But sometime. But the point is that you can follow other people to their death, which is an extreme case. You're just following somebody else and you're not learning, is what my point, okay? Do it for yourself. Don't just copy what I did. The effect of independent variable on the dependent variable, okay? All right. So I have a proper title now. Okay, I've got a proper axis label on the X and Y, or the horizontal and vertical, because technically they're only X and Y for using X and Y. All right. Now, when I was working in this graph area, I had it highlighted. It was kind of gray. If yours is gray, click in there and make it white again. All right. And now we're ready to copy the graph to put in the report. So I'm going to right click in the white space over here. If I right click in here, sometimes it'll change the color on me. I like to go over to the white space because it works out a lot better. And just right click. And then you got an option to click copy. Okay, you can also click in that space and use a shortcut on your keyboard, Control C. All that works. But I want to copy it so you can see what I'm doing. And I'm going to go back to the report I was working on. And in the correct spot, let me go down here and just find the new page, maybe. All right, and I'm going to paste. In this case, you can do it several ways. You can go to Edit Paste. You can Control V. I want to use right click and paste. And just wait a minute, and there's the graph. I'll take it back, zoom it out just a little bit so you can see a little better the whole graph. Okay, there's the graph. Does that make sense? Yes.
Mine never even graphed. Oh, no, I can't get it to.
You probably just skipped some step somewhere. More than like, if you got Logger Pro, it's, I'll try and help you in a minute if I can, okay? But if you follow the steps, it should all work. All right, now, we're still missing a figure label. A graph without a figure label is not a complete graph, or not for a report anyway. So I'm going to click on the graph. I'm going to hit my right arrow on my keyboard, and then I'm going to hit enter, and I'm ready to start typing a figure label. Okay, figure 1, which is the first graph in my report. I want to describe what's in there, why it's important, and what the analysis is. Okay, so what's in there? This is a graph of the graph. How about that we say that compares? Okay, that's what's in there. All right, but I've also stated in that sentence why it's important. Because I've stated we're seeing a resulting change in density. Okay, now when you say there's a resulting change in density, you're saying by that, inferring by that there is a causal link. Okay, there is a cause. The change in the amount of salt caused the change in density. Don't write a causal statement when there is an actual cause, okay? All right. Sometimes you're just comparing two sets of data, and it's not really one thing causing another. But your independent variable is what you change. The dependent variable, which we graph the independent variable on the horizontal axis, the dependent variable on the vertical axis, that's the expectation. If for some reason it's not done that way, you need to explain that. If it's done that way, you don't have to explain it because that's what's expected. All right. So we're saying there's a cause by doing it that way, by writing it this way. All right. And so what is the result? All right. Spelling is an issue here. All right. Change it to and change that to the. Okay. All right. There's maybe take that out. So there's a direct relationship between the addition of salt and the density. The word direct describes the type of shape we have here. There are two types of graph shapes for which we have names that you need to know. Direct is one of those two. If the best fit line is the best fit line or curve, the best fit curve is a straight line and has a positive slope that indicates a direct relationship. The word is direct, okay? There's also an inverse relationship we'll get to later. An inverse relationship is a curve with a negative slope. This is a positive slope, okay? Does anybody not know how we know it's a positive slope? Okay. If we were to write, well, in fact, come to think of it, the data's right here. Let's go back to the graph. D equals mx plus b. That's the shape of that's the mathematical formula for a line, right? For a straight line. Which one of those numbers, well, it says m is the slope. It's a positive number here. That's what I mean by positive, shape, positive slope. All right. If it was negative, the line would be going down instead of up. All right. Let's see, report. I want to go back to this. Okay. So don't write exactly the same thing that I wrote for the figure label. Okay, because that's plagiarism. Write your figure label. Okay, your words. You say basically the same stuff, but you don't copy somebody else's stuff. Besides, when you copy what I wrote, again, you're not really learning how to do it. You're just copying something. Okay, you're a lemming. Okay, don't be a lemming. Look it up. Okay, all right. So that's how we did the graphs. And then this is a standard curve or a calibration curve. Either phrase works fine. They actually mean slightly different things, but in the context of this, it's not significant. To find what the concentration is of the unknown. All right? Any questions about that? Your conclusion then should explain how you determined what the concentration of the unknown is. To do that, you've got to explain how you created your calibration curve. That makes sense? If you don't explain how you created your calibration curve, you're not explaining how you found the concentration of the unknown. Any questions about all that? All right. I'm sorry for those of you whose Logger Pro isn't working yet. That you just I've got this recorded, by the way, so you can go back and look at this when you fix it. Okay. All right. Questions? Any further questions? All right.
All right, let's talk about how science really gets learned.
So there's this thing called the scientific method that you've all heard about before. And in the scientific method, you start with some kind of problem, or you start with some kind of goal, and you write an hypothesis on what you think is going to happen. And hypotheses are, if I do this, I expect this to happen. But hypotheses can be things that you don't control. You can't actually manipulate variables to get there. It might be something in nature where it has to do with animals or the weather, okay, or geology, and you can't manipulate those things to get an answer. And then you do some kind of experimentation, or you gather data from nature where you can't actually directly experiment, right? And then you reach some kind of conclusion based on the results. That's a great set of steps, and it's very valuable and very helpful, but in a very real way, it's wrong. And the word "the" is what's really wrong with it. And the other thing is sometimes conclusions at the end are not as easy as all that to come up with. So I want you to think about the scientific method as being a nice guideline, an important guideline, and the steps are really essential steps, but there is no the scientific method, okay? A better term might be scientific methods, but it's kind of hard to teach scientific methods, plural, because there are so many different ways of doing science, okay? If you were to think of one name that is the epitome of all scientists, what name would that be? Huh?
Isaac
Newton.
Newton.
Wow, this is probably the first time somebody mentioned Newton first.
Einstein.
Einstein? Okay. The reason that Einstein usually comes up first is just a big name, right? Einstein actually showed that Newton was wrong. Okay? Pretty cool, though, that you came up with Newton, all right? Einstein didn't follow the scientific method. He didn't do any independent measurements or experimentation, okay? He basically went straight to the end. He started with the data, things that are already known, and went straight to the end where you reach a conclusion. He skipped over all that. Does that mean he's not a good scientist? Absolutely not. He was a genius scientist, okay? But he did science in a way that doesn't fit the scientific method. So what I want to talk about is how science really gets done. Fair enough? Okay? This is what I want you to remember all that stuff. You've learned all that before. I'm not going to reteach the scientific method. I'm reminding you about it. But I do want you to know how science really gets done, okay? So on a piece of paper, and I would use a big piece of paper and put this right in the center of it, I want you to put the goal of science. All right? And what is science really all about? What is it that we're trying to, if we're using the scientific method, what are we trying to get with science? What's the point? Why do we have science? Nobody knows? This is a question for you. It's not a rhetorical question. It's an actual question for you. What is science supposed to be about? What are we doing with science? Prove laws? Actually, it's kind of bigger than that. Finding out the unknown? Yeah, but it's really bigger than that. Huh? Laws of the universe? Well, it kind of goes along with that pretty well, yeah, but there's more to it than that. Explaining unknowns, yeah, there's a specific way of explaining unknowns, okay? So it's laid out in a way that scientists accept, yes. Boy, she nailed it, okay? to develop defendable arguments to explain the way the universe works. So it's not just explaining the way the universe works, because you know what? Scientists don't know. We're trying to come up with defendable arguments for the way the universe works. Here's the problem. Newton came up with laws that explain the way the universe works, defendable laws, or defendable, well, actually laws. The theories underlying that are even bigger than that. But Einstein showed that those laws don't always work. Okay? So, but he had a defense for it because it worked. Okay? Einstein had a defense for it because it worked. He could show how that it actually does what we think it's supposed to do. And a lot of the things that Einstein proposed have been shown by evidence to be defendable since his death. Okay, so we keep finding new information, new data, new experiments that show Einstein was right. We also have some new experiments that show Einstein may not have been completely right. But you know, we're not showing how the universe works. We're trying to get there. We're always trying to get there. Does that make sense? It is a constant forward-moving effort to try and find out how the universe works, but we're writing these defendable arguments. When we say defendable, that means they're based on observation. You can observe or you can measure, you know, it might be this measurement leads to this measurement, leads to this measurement, or leads to this calculation, leads to this conclusion, but eventually we get there. So these arguments have to be made based on natural explanations, physical evidence, physical explanations, and sound reasoning. Sound reasoning. Some people, I'm not so sure about sound reasoning these days. Sometimes I hear some stuff that's like, what? Where do you get that from? Okay. So we're going to leave that kind of as an open-ended thing about what's sound, all right, for right now. Okay, reasonable. And it's scientifically reasonable is what's important. Well, how we get to all this starts, or you could say starts with, it may or may not start with, because it's really a circuitous process. We organize what we know. We can't find out new stuff until we know what's already known. Does that make sense? Einstein came up with his theories, laws, based on what other people already had found out. They were written down in books then. Now they're written down on the internet, or maybe in books. They're written down somewhere. They're explained by somebody somehow. But it's organized so we can kind of figure out what's going on. Okay? So if we don't keep up with what we already know, we can't move forward. We're reinventing the wheel. And why do we want to reinvent the wheel? Okay, it's already invented. We don't need to reinvent it. All right? So we're organizing what we know and what we'd like to know. So that may be a beginning place, or maybe it's just one of the steps, stepping in the stepping stones of life. I don't know. All right, but then from the data we have, we are going to generate hypotheses. So we talked about that in the scientific method discussion a moment ago. We're trying to figure out what proposed results do we expect from experimentation or from some kind of field testing. But there's a word in this statement that you may not be so familiar with. Okay, right at the very end, model. What in the world is a model? Well, this model is not an attractive person wearing clothes that walks down some runway, okay? Or who poses for pictures in a catalog, all right? Not that kind of model. Not the plastic that you glue together that ends up looking like cars or ships or planes, okay? This model has to do with behavior, the way things occur, the way things happen. And we sometimes don't give it the credit we need to give it in the sciences. It's sad that you get to a high school chemistry class, and how many of you know what a model is? Raise your hand. One, okay? One out of a class of almost 30 kids? Really? See, to me, that's kind of sad. You really should know what a model is. It's how we think things should be thought of as happening. It doesn't mean it's right. It's a way of constructing process, okay? It goes to that statement we talked about earlier, cause. What would cause something to happen? Now, I use that very specifically, and models are really broader than that, but I use the word cause as the specific element that needs to be part of your model. If you're writing a model for me in the chemistry science, you need to write a statement for why or how things happen. Okay? That's my model for this class. In other sciences, model can take different forms. So while I need you to be locked into the word cause for this class, I don't want you to be locked into it for other types of science. Okay? It's the mechanism we use for figuring things out. All right? Model. So from that organizing step to generating hypotheses, we're going to have a model. To get from one to the other, we got to have a model. We don't write an hypothesis without thinking about, and in our minds at least, in the background, understand what causes it to happen. Okay? You don't write an hypothesis without a cause in mind. All right? And both of these go to the goal of science, which is developing those defendable arguments. From the hypothesis, which is from or includes a model, which is built on what we know and what we want to know, we're going to seek evidence. Now, that might be experimentation, or as I said, it might be going out in the field and gathering information in the field. Okay? But now, gathering information doesn't show the model to be true. It only shows the hypothesis to be true. This is a difficult thing for a lot of people to understand, not just high school students, people. Okay? The model goes to what's causing it to happen. The hypothesis is only going to what is happening. Okay? While we know things happen, figuring out why, that's the tough part. All right? What does happen goes to laws. What causes it to happen goes to theories. Okay? Theories don't give you laws. Theories explain laws. And that's part of explaining the way the universe works. That's part of that defendable argument. Okay? The laws of what do happen, the theories are why. And we can't prove theories. The fact is, if somebody uses the word prove, and if they're explaining something in science, they don't really understand science, because science doesn't prove things. Okay, we're trying to figure it out all the time. And we hope we're right about it, but we always hold out that option that it might be wrong. Okay, it could be wrong. It might, almost certainly right, but, there's that possibility. Just like Einstein's theories, there's some people who are thinking it doesn't always work all the time. Even Newton, we know to be right for most things, but when you get to extreme cases, it doesn't really work anymore. All right, then we're going to go to constructing an argument. We've done testing, we've sought evidence. We're going to construct the argument, and that's a tough thing. You think constructing an argument's easy, right? Maybe. And the science is not. In the sciences, it's not. In the sciences, we have something called peer review. Now, you've done peer review before, probably in an English class maybe. You write a paper and have somebody else read it and give you some feedback, right? In the sciences, it's a lot more than just correcting your grammar. It's going right to the heart of what you've figured out. You know, they're looking for whether or not your law or your theory or your hypothesis really stands up based on those, the data you have, and the information you have, and the theories that exist. They're ready to shoot it down. And it's harsh. I mean, scientists are not sometimes the nicest people about questioning your process or your conclusions or your evidence. Okay? But we're trying to get to the real important stuff. And if somebody's discovery, quote unquote, doesn't stand up to that kind of scrutiny, then it needs to be investigated. It needs to be evaluated. It needs to be shot down if necessary, or at least fixed. Because that peer review process is part of fixing things that don't work well, that really don't stand up to the scrutiny we want it to stand up to. When we get to a point where we can call something a scientific theory or a scientific law, we want it to be as solid as it can be based on the evidence, the physical, observable, measurable evidence. Okay? So we want to make sure we've got everything right as best we can, given the fact that we know that it can change if new evidence comes along. So constructing the argument is a harsh process sometimes. But when you go from the hypothesis to that, you take the evidence you have, you write it up, go through the peer review process. Maybe you publish it somewhere and people write nasty things about it. Not nasty things, nasty. Because in the sciences, it may be harsh, but we don't mean it to be nasty, okay? Not in the sense that people use the word nasty, all right? It just means it's harsh. It's tough because somebody's invested decades of their life trying to figure out something and other people are finding things wrong with it. But we need to find out what's wrong with it, you know? There really have been scientists that have attempted or succeeded in committing suicide over stuff like this because it's their life. They've built their life around this idea, this work they've been doing, and somebody finds it not quite right, you know? Some famous scientists have come up with some really important discoveries, and a lot of the scientific world said, that doesn't work. It can't be true. It doesn't make sense. They might turn out to be, the body of scientists might be wrong, and that's been shown to be true too. Okay, but also it's true that it gets shot down and it stays shot down. All right, and so then we go back to the beginning, because every time, hold on, don't pack up yet. Listen, please. I will try to give you some warning about when to pack up. But when you start packing up, the next person starts packing up, noise gets, people get distracted, and nobody's paying attention anymore. And this is really important. Okay? Every time, there's an old proverb that every time you find out something new in the sciences, you post 10 new questions. There's some truth to that. It might not be 10, it might be 100, or it might be 3. But every time something new is discovered, there are new questions. Science never stops, it keeps going. But this is the process through which science actually gets done. There is no "the" in scientific method, but that step-by-step thing you've learned is still valuable because it is a good pattern to follow. You just got to know that sometimes you don't have to actually follow that pattern sometimes. The hard thing is knowing when you can and when you can't. You follow me? So everybody knows what they're doing tonight, right? You're doing some research. You've got to have things written down, okay? But I don't want you to sit there and read things tomorrow in the discussion. But I want you to be familiar with what you found well enough to talk about it. I mean, you can look at it, that's fine. You can look at your notes. But don't sit there and read stuff to me, all right? That makes sense? Yes.
Do you want us to have it like on a Google Doc or written on a piece of paper?
Eventually, it'll have to be on a Google Doc. But for tomorrow, you can decide how you're going to use it, what form works for you.